Okay, so this is going to be Unit 3, Notes 2. Just as a review, what we did in Notes 1 was talk about ionic compounds where we had a metal that created a positive ion mixed with a nonmetal that created a negative ion. So we mixed that positive metal with a negative nonmetal, and that created the ionic bond. And remember, in the ionic bond, we had a donation of electrons. The positive metal became positive because it donated that electron over to the negative anion or the nonmetal. So in this set of notes, what we're going to do is actually cover a different type of bond, and that is going to be called a covalent bond. And we're going to take a look at covalent compounds specifically. So let's go ahead and begin with that. So what exactly is a covalent compound? Well, covalent compounds are basically when we have atoms that instead of donating electrons, they're actually going to share them in between the two atoms. Okay, so instead of donating from one transferring over to the other, is going to be sharing electrons instead. And this occurs for them to become stable. Now, unlike the ionic bonds that have a metal and a nonmetal, covalent compounds are formed only between nonmetals. Okay, so no metals here. So they are usually formed between two or more non-metals only. All right, so keep that in mind. If I ask you in the future, what type of bond has only non-metals, then of course we're going to be talking about covalent compounds. Here are some properties of covalent compounds. They exist in solid, liquid, and gas forms at room temperature. It really depends on what type of elements you're going to be mixing, but they do exist in all sorts of different compounds and different states of matter. They normally do not conduct electricity because they are insulators. And again, the reason why they do not conduct electricity is because they only contain nonmetals. And if you remember from way back in Unit 2 when we were talking about the properties of different elements, nonmetals do not conduct electricity, but metals do. So because covalent compounds don't contain any metals, they're not going to conduct any electricity. All right, so how do we name covalent compounds? Well, it's a little bit different than what we've learned in ionic compounds, but not too much different. So if you remember from ionic compounds, what we had to do was change the ending of the last element to "ide," I-D-E. All right, well, that's still going to hold true here, but we're also going to use these things called prefixes, and the prefix is a thing that comes before the word, and we're going to use these prefixes in the names to determine the subscript in the formula. Okay, so these are, I believe, are going to be Greek prefixes for different numbers. So we have mono, di, tri, tetra, penta, hexa, hepta, octa. All right, so like a triangle has 3 sides. An octagon has 8 sides. A hexagon has 6 sides, right? If you've ever played Tetris, you might notice that every single piece in Tetris is made up of 4 blocks, right? So that's where tetra comes from. So the name of the second element still ends with the suffix "ide," so we're still going to change the ending like we did in ionic compounds, but we're also going to add this prefix to the name. Okay, so here we have an example: carbon monoxide. Okay, so carbon refers to just the element carbon, and then monoxide. So we just kind of combined it so that it's monoxide. That means one oxygen because mono means one. Right there. So monoxide, we're going to add that prefix to the beginning of the second element. All right, so that's how we would write carbon monoxide. One carbon, one oxide. Okay, why don't we call it monocarbon monoxide? Well, for some reason the rule doesn't apply. The mono doesn't apply to the first element, but all the other numbers, prefixes, do apply to the first element as well. Mono is the only one that doesn't apply to the first element, but it does apply to the second element. All right, so let's see if we can figure out what dinitrogen tetrasulfide is. Dinitrogen should be pretty easy. We have nitrogen as the key word here, and that's going to be the element nitrogen, which is labeled with the abbreviation N, capital N, and then di means that we have 2 of them. So if you take a look at this numerical prefix chart, di means 2. All right, so that we have N2, and then tetrasulfide. Sulfide comes from sulfur, which is labeled S, and then tetra means 4, right? So if we see tetra means 4, so we have N2S4. All right, so that's how we would write that, N2S4. So here are some exceptions to the rule. We could call this nitrogen trihydride, and this is carbon tetrahydride, but these actually have some names. So these are things that we just call by their normal names. So we have ammonia, NH3 is ammonia, CH4 is known as methane, H2, O2, Cl2, and F2. These are all examples of diatomic elements. There's 7 of them, but these are ones that we just call by their diatomic name. So we have hydrogen, oxygen, chlorine, and fluorine because they're almost never found by themselves. And then, of course, we know H2O to be water. We learned this one to be dihydrogen monoxide in the last series of notes. It is a covalent compound, and that's how we would name it, dihydrogen, because we have 2 hydrogen, and 1 oxygen would mean that we have monooxide. All right, so let's go ahead and take a look at some practice problems right now. We're going to take a look at practice problems 1 and 2. All right, practice problem number 1. Go ahead and pause the video right now, see if you can answer some of these on your own. And then we're going to go through them together. But I'm going to go ahead and get started. And we're going to take a look at some of these. And what we want to do is come up with a formula based off of the name of the covalent compound. All right, so we're going to start off with the first one. And it says antimony tribromide. So if I take a look at the periodic table and I try to find antimony, it's right here. It's labeled as SB. All right, so I'm going to put S and then B. And then I notice that it doesn't have any numerical prefix, no mono, di, tri, whatever. So basically what that means is there's only one of them. And remember that the mono doesn't apply to the first element. So we wouldn't say mono antimony, it would just say antimony. But now we have tribromide. Bromide, of course, comes from bromine, which is this element right here. So that's going to be Br. And then the tri means that we have 3 of them. Because if we look at our table, tri means 3. All right, so the next one is called hexaboron silicide. And again, we want to take a look at the nonmetals here to find the formula. So hexaboron. Boron is this element right here. It's abbreviated with the letter B. And the hexa indicates that we have 6 of them, right? So hexa means 6. So I'm going to put a 6 right there. And then silicide comes from silicon right here, Si. Now notice there's no prefix for this one. There's no mono, di, tri. If there is no prefix, you can again assume that it means 1. Now typically we would have a mono here for the second part of the name here, for the second element. We'd have monosilicide. And that is actually another name for hexaboron silicide. There's another name for it called hexaboron monosilicide. Just in this case, both happen to be correct. All right, moving on to the next one, we have chlorine dioxide. So chlorine is just Cl, we know that one. And then dioxide. Oxide, of course, comes from oxygen, so that's ClO. And then di means that we have a subscript number 2 right there. Hydrogen iodide. Okay, so we have hydrogen, which is the only nonmetal on the left side. So this is where hydrogen is. Notice it has a blue border next to it because it is a nonmetal. So hydrogen is just by itself because there's no mono or anything. There's no di, tri, or any other prefix. And then we have iodide. Okay, so iodide is by itself. And again, this is another case where we could have monoiodide in there, but in this case, it's just simply known as hydrogen iodide. So it's just Hi. Okay. Then we have iodine pentafluoride. So we have iodine and no prefix, and then pentafluoride. So here's fluoride is F from fluorine, which is right there. And then penta means it has 5. All right, this one, dinitrogen dioxide. So we have nitrogen as our first element, so nitrogen. And di means that we have 2 of them. Oxide comes from oxygen. And we also have 2 of those because of that prefix. All right, ammonia was one of those special ones, so you have to kind of refer back to the notes. That's one that has a very specific name. Ammonia is a substance that is well known, and we know the chemical formula as NH3. So NH3 is ammonia. You could also call it nitrogen trihydride. That's another name for ammonia, but in this case, it does have a specific name, similar to how water is called water and not dihydrogen monoxide. All right, and the last one here for practice problem number 1, phosphorus triiodide. So we have phosphorus, which is P, and then triiodide. Iodide comes from iodine, and then we have 3 of them, so we're going to put a 3 right there. All right, so these are all of the formulas that we have written out for all of our the names for practice problem number 1. Okay, so practice problem number 2 actually has us working backwards. So now what we're trying to do is find the name for the compound given the formula. So just like what we had with the ionic compounds, we want to leave the first element in the compound just the name of the element. All right, so if we take a look at the formula P4S5, P is the element phosphorus. It's right here on the periodic table. And we're just going to leave it as phosphorus. So I'm going to go ahead and start typing it out. Okay, it's actually OUS. But we want to account for that it has 4 of these. So there's 4 phosphorus. And so we have to include that prefix. The prefix comes before the word. So we're going to leave in the prefix right there. So it's tetraphosphorus. So that's the first part of the formula name, is we're going to take the element, just the element name, and then add any prefixes if we need to. The second element is going to have that ending change, where the ending does change to the IDE, just like it did with the ionic compounds. So sulfur is the element S, so it's SULFUR, but we're changing the ending to "ide", so it's going to be sulfide. Now we do have 5 of these, so we need to include that prefix in the beginning. So that's going to be pentasulfide. So that's the answer for the first one. It's tetraphosphorus pentasulfide. We're going to go down the list now. So we have O2. Now O2 by itself is just oxygen. And the reason why I know that is because it is one of those diatomic elements. Remember, a diatomic element is an element that exists by itself in a pair, so it's always going to be paired up with another one. Just as a review, which elements are going to be the diatomic ones, I'm going to highlight them for you. So it's nitrogen, oxygen, fluorine, these ones, and then these ones right here. And then there's also one more, it's hydrogen up here. All right, so these highlighted elements that I just highlighted, these are the diatomic ones that always appear in pairs when they're by themselves. All right, so oxygen, when it's O2, is just called oxygen. That's it. It's got a special name, and we could leave it as that. All right, the next one, SeF6. So again, the first element we're just going to leave by itself, and Se is found right there on the periodic table, and it's called selenium. And then F6. So F is going to be fluorine, but we're going to change that to fluoride. And then the 6, remember we have the prefix, so we have to add that in the beginning, is going to be called hexafluoride. Selenium hexafluoride is the name for this formula right here. The next one is going to be Si2Br6. So Si is going to be silicon. But we have a number here. We have the 2 going to that silicon. So that's actually going to give us the prefix disilicon. And then what we want to do is account for the bromine, which changes to bromide. And then we have 6 of them. So that's hexabromide. Disilicon hexabromide. The next one up here in the top right, we have sulfur as our first element. So we're just going to type in sulfur. And then there's only one of them, so we don't need to put in the mono because that doesn't apply for the first element. And we have chlorine next, but that changes to chloride. And how many of those do we have? Let's go ahead and start adding the prefix ahead of time. It's tetra, and then we can say it's chloride. So sulfur tetrachloride. All right, so this next one, it's CH4. If you answered for this one, carbon tetrahydride, well, you wouldn't be wrong, but you're not actually 100% right. So this is one of those special occasions where this specific formula, this compound, does have a specific name. And carbon tetrahydride is technically a correct name for it, but we also just know it as methane. Right, so methane is technically the correct name for CH4. All right, next up we have B2Si. B2 is going to be that's going to be boron, but the prefix 2 is associated with di, so we have diboron. And then Si is for silicon. We could just call it silicide, okay, diboron silicide, or we can also call it diboron monosilicide. NF3, so we have nitrogen just by itself, so we don't need to add mono there, is nitrogen. And then F3, so 3 represents tri, and then F represents the fluorine, but we're going to change it to fluoride. So this last one is nitrogen trifluoride. So now we're going to take a look at a topic that we looked at in ionic compounds that also applies to covalent compounds, and that's the dot diagrams, or also known as the Lewis structures. So these dot diagrams are just a representation again of how electrons are spread out and how the actual atoms are bonding to each other. So in covalent dot diagrams, the atoms share electrons to satisfy that octet rule that we mentioned briefly in ionic compounds. Remember that the octet rule basically means that each element wants to have 8 valence electrons, or in some cases for smaller elements like hydrogen, it's only 2 valence electrons. Most elements want 8, but hydrogen in particular and some other elements only want 2. So we use lines in these dot diagrams to represent 2 electrons that form a bond between the atoms. And typically when we have a line like this, let's take a look at the hydrogen. We have hydrogen, which only has 1 electron, and this other hydrogen also has 1 electron. Now I mentioned before that hydrogen only wants to have 2 as the number of valence electrons. So what these 2 hydrogens are going to do is that they're going to buddy up here and they're going to share 1 electron each. So this line actually represents 2 electrons, one coming from this hydrogen and the other coming from this hydrogen, and they are both in possession of these 2 electrons. It's very similar to, like, if I were to create an analogy for this, let's say you have this is you and this is like a sibling that's very close to you in age. You might have a sibling like this, you might not. But let's say one sibling owns a certain toy or gaming console, and the other one has a different one, and they're both being able to share with them. So they're going to be able to share back and forth and use those resources with each other. They both own it. All right, so for covalent dot diagrams, it's basically, again, the lines represented the electrons, and sometimes we do have what's called a pair of electrons or a lone pair of electrons represented by these little dots. So this oxygen here has 4 extra electrons just hanging out, and then each line represents 2. So for oxygen, it has 1, 2, 3, 4, and then the line represents 2, so that's 5, 6, 7, 8. So this oxygen now has 8 valence electrons. So let's take a look at a few examples of covalent dot diagrams. For the first example, we're going to take a look at water, like I was just explaining. And what we want to do is draw the individual atoms first, placing dots representing the valence electrons on each atom clockwise. So that's the first step. Go ahead and draw out all of the elements that you're going to be dealing with. So we have 1 hydrogen, and we drew out its 1 valence electron. Then we have another hydrogen, and we have another valence electron like this. And then we're going to draw the oxygen clockwise, drawing out the valence electron. So we have 1, 2, 3, 4, 5, 6. And just to recap, how do we identify the number of valence electrons? We use that little trick where we count the tall columns on the periodic table going from left to right, and it goes from 1 to 8. All right, so we have 1, 2, 3, 4, 5, 6 for oxygen, 1 for hydrogen, and 1 for hydrogen. And now instead of donating, so instead of like hydrogen donating its electron to oxygen, they're now going to share. All right, so this is how it's going to bond together. So we are going to connect the dots so that every atom satisfies the octet rule. All right, so now hydrogen technically has 2 because it's allowing oxygen to access this one. So it's sharing with oxygen here, but it's also grabbing one from oxygen to share for there. So hydrogen has 2, and remember hydrogen only needs 2, in order to satisfy its rule. So hydrogen's good. What about oxygen? Oxygen now has 1, 2, 3, 4, 5, 6, and 7. So it's actually sharing with this hydrogen here, so it has 7. So then now it needs to bond one more time. So it's going to bond to this hydrogen right here. So this hydrogen is good as well because it has 1, 2 electrons it has access to. This hydrogen has 2 electrons it has access to, and this oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons that it has access to. So now it's pretty happy. It's satisfied the octet rule. So remember that the lines are 2 shared electrons and both elements have access to both electrons in a line. So hydrogen has access to both of these, but so does oxygen. Right, now we drew out the model kind of sloppy, so in a typical sense we wouldn't draw out the dot diagrams like this. For dot diagrams, you want to clean it up. You want to clean up your final drawing so that the actual molecule itself has only 90-degree angles. And we also want to make sure that we check for the octet rule. So hydrogen has 2, that's good. Hydrogen has 2, and then oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So that's good. And of course we have that 90-degree angle. We also don't actually need to include the electrons on the lines. Some people do this just to show or just to remember that each line represents 2 electrons. But in a typical sense, we know that every single line is going to represent 2 electrons. So there's oxygen and has 8 electrons, and each hydrogen has 2 electrons. So we're good. Let's take a look at O2, which is just diatomic oxygen. So we're going to follow the steps again. The first one being write out the elements and then draw the valence electrons around it. So we have oxygen with its 6 valence electrons, and then we have another oxygen with its other 6 valence electrons. Right, so what they're going to have to do with each other in order to pair up is to share electrons. If they have 6 and they want to get to 8, that means they're each missing 2 electrons. Right, so what they're going to do is, like, let's say we can pair this one up. They're going to share here. So now this oxygen has 1, 2, 3, 4, 5, 6, and then if we follow this line, 7. So it's sharing there. And the same thing with this one, 1, 2, 3, 4, 5, 6, and then sharing 7 here. So we're pretty close to 8, but not quite yet. So let's bond one more. So let's bond to this one. So now oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And this one has 1, 2, 3, 4, 5, 6, 7, 8. So now they're good. But we're not quite done with this model because it does look a little bit sloppy. So we want to clean it up so that it kind of looks like this. The outer electrons don't really matter where you put them as long as they come in pairs, or the best way you can put it is as pairs. And then we have the bond in the middle here, which is kind of like this double bond representing a total of 4 electrons. So 1, 2 for this line, 3, 4 for this line. That's a double bond representing 4 electrons, and they all satisfy the octet rule. All right, so let's take a look at practice problems 3 and 4, and we will work on some dot diagrams. All right, so practice problem number 3 wants us to draw out these dot diagrams. So go ahead and pause the video, see if you can do some of these on your own. It might take a while because they do take a little bit of time to kind of perfect and master. But come back to this and then we will start reviewing. But I'm going to go ahead and get started here. And we're going to start drawing the dot diagram for the following compounds. The first one being ammonia. All right, so the first step that you want to do is, again, write out all of the elements that you have. So we have nitrogen, and we will also want to account for the number of valence electrons. If you don't remember the valence electrons trick, again, it's just counting all of the tall columns from left to right. So 1, 2, 3, 4, 5, 6, 7, and 8. So nitrogen is in column number 5. That means it's going to have 5 valence electrons. 1, 2, 3, 4, 5. Okay, and then we have 3 hydrogens. And hydrogen only has 1 valence electron. So we're going to put 1 hydrogen there, the second hydrogen there, and the third hydrogen there. All right, and then the next step is to start connecting the dots so that we have all of the the elements satisfying the octet rule. Okay, so hydrogen only needs 2, but nitrogen does want to have 8. All right, so we're going to try to connect these two. We can maybe connect these two, and then maybe these two right here. So let's see if hydrogen meets the octet rule. So hydrogen only needs 2, so it's connected to one line each, and each line again represents 2 electrons. There's 1 right there, and 2 right there. 1 right there, 2 right there. 1 right there, and then 2 right there. So each hydrogen connected to 2 electrons, they're all good. But what about the nitrogen? Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So it's good. The final step is we can go ahead and start cleaning this up a little bit so it looks a little bit neater. So something like this with 90-degree angles. We don't actually need to create the electrons on the end of these lines. And then we also do want to include any lone pairs, or like a pair of electrons that are not bonded to anything. So there's 1 electron here and 1 electron there. They're not bonded to anything, so we're going to put them right there. Right, so we wouldn't want to necessarily submit this or anything for like a homework assignment, or because that's not a proper diagram. The proper one looks something like this, where it's all cleaned up and it's much easier to see what's going on. All right, next up is fluorine, which is F2. So fluorine, we're going to write out the symbol, and then it has 7 valence electrons because it's in column number 7. And then it has 1, 2, 3, 4, 5, 6, 7. And then that's 1 fluorine. And then we have 2 fluorines. 1, 2, 3, 4, 5, 6, 7. So now what we want to do is start connecting the dots until they both have 8. Well, it's not going to take much because they all have 7 and they both want to have 8. So if they just share 1 with each other, they should be good, right? So if we just draw one line connecting the electrons, so now they're both sharing. This fluorine has 1, 2, 3, 4, 5, 6, 7, 8. So that's good. This fluorine has 1, 2, 3, 4, 5, 6, 7, and 8. So that's good, right? So final step is just to clean it up. So we have F for fluorine connected to another F for fluorine. And then we're going to draw out the other 1, 2, 3, 4, 5, 6 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we can kind of erase our rough draft here. I'm just going to select, I'm just going to be able to move all of this. There we go. All right, next up is phosphorus trichloride. So we have PCl3. So let's go ahead and draw out the phosphorus. It is in column number 5, so we want to identify the number of valence electrons, and it has 5 valence electrons. 1, 2, 3, 4, 5. Chlorine, Cl, has 7 valence electrons. So it's in column number 7. So we're going to draw out 7. 1, 2, 3, 4, 5, 6, 7. And let's see if I can actually just copy and paste this. So I'm just going to copy and then paste. Let's see if I can move that. And then paste it one more time. Okay, so now what we can do, now that we have these 3 chlorines, these chlorines have 7. They only need 1 each in order to satisfy their octet rules. The phosphorus has 5 and it wants 3 more in order to satisfy its octet rule. So what you can kind of predict is that the phosphorus is going to match up with each chlorine. So something like that. Okay, so now does this phosphorus have 8 electrons? Let's check. 1, 2, 3, 4, 5, 6, 7, 8. It does. So this phosphorus now has access to 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 for this chlorine. 1, 2, 3, 4, 5, 6, 7, 8 for this chlorine. 1, 2, 3, 4, 5, 6, 7, 8 for this chlorine. Now, this is kind of a difficult one to see because we have a lot of overlapping um, elements, and we have a lot of elements just kind of floating around. So what I'm going to do is kind of highlight the elements that belong to each atom, and you'll notice that there is a lot of overlap. So this chlorine contains all of these electrons here. Okay. This chlorine contains these electrons right here. And then let's do one more. This chlorine contains all of these electrons right here. Now the phosphorus contains all of these electrons. So what you can see here is that there is an overlap with what electrons are being shared, right? But it's not quite this messy. What we're actually going to be able to do is clean this up a bit. So let's just maybe select this whole thing. Let's see here. I'm just going to move this off to the side, move this back. And then what we can do is actually redraw this so that it's a little bit cleaner. All right, so let's go ahead and do that. We have phosphorus in the center. It's going to be bound to a Cl here, Cl here, and then Cl here. And then each Cl has 1, 2, 3, 4, 5, 6 electrons around it. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then phosphorus has just 2 electrons kind of floating around, not bonded to anything, so we're going to put them right here as a pair. So you can see just how much cleaner that looks versus this model right here. I'm going to go ahead and erase this so we can just focus on the next problem. So methane, CH4 is the next one. What we want to do is go ahead and write out the carbon right here. And carbon has 4 valence electrons because it's in column number 4. So I'm actually just going to put 1, 2, 3, 4 carbons like that. And then the hydrogens, hydrogen only has 1 valence electron. So it's right there. And what I'm actually going to do is you can kind of guess. I'm going to put hydrogens on each side of those electrons that I drew out for a carbon. Okay, so hydrogen only needs 2 electrons, so it's going to bond with carbon right there. This one's going to bond to this carbon right there. This one's going to bond to this one right here. And this one's going to bond right here. So what you can see here is that this carbon is now bounded to 4 different hydrogens, and each hydrogen is satisfying its role by only needing 2 electrons, and carbon has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. All right, bromine is next. Bromine is in column number 7. It has 7 valence electrons, and there's 2 of them. So this is actually very similar to this problem that we were working on with fluorine, because fluorine also had 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. Actually, this is Br. My mistake. And then we have Br again. So 1, 2, 3, 4, 5, 6, 7. Okay, so they each have 7. They want 8, so they're going to bond just 1 time so they can share 1 with each. And that's pretty much it for bromine. Nitrogen has 5 valence electrons, so we're actually going to go draw out 2 nitrogens with 5 valence electrons. Now I'm kind of going to break the rule here. Typically you would only draw 2 per side. I'm going to break the rule and put 3. 1, 2, 3, and then 2 here. And the reason why I'm doing this is because I already know what this is going to look like, and I don't want to have to clean it up again later. So this is actually, once you practice this is enough, you kind of get an idea of what's going to happen. So we know that nitrogen has 5 valence electrons. They're going to need each 3 more in order to get to 8. So these nitrogens, they're going to share this top one, they're going to share this middle one, and they're going to share the bottom one. All right, so now if we do that highlighter trick again, we can do this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. It has all of these electrons. This nitrogen contains 1, 2, 3, 4, 5, 6, 7, 8. So you can see how the colors kind of overlap here and how they're sharing. And this nitrogen has created what's called a triple bond. So we haven't covered that yet, but this is a triple bond. Whereas the bromines, right here, they only have a single bond. Okay, there is a double bond that exists, and the highest bond actually is a triple bond. So the question might be now that if I ask you what bond is going to be stronger, is it going to be the single bond between the bromines, or is it going to be the triple bond between the nitrogens? Well, if you did this little test where if you linked up your fingers like this, if you only linked up one finger and pulled them apart versus 3 fingers, so if you're linking 3 fingers, it's much harder to rip apart 3 fingers than it is 1 finger. So you can kind of do that test. The triple bond is going to be significantly stronger of a bond than the single bond is for the bromine. Practice problem number 4 wants us to find the errors in the dot diagrams below. Okay, so the first thing that I would check, I'm actually going to type this out for us. The first thing I would check is check if each atom satisfies the octet rule. But we have to remember hydrogen only wants 2. Okay, so that's the first thing that we will check. The second thing that we would check is, did each element start with the correct number of valence electrons? Okay, so that's the second thing that we would check. So for the first one, we have N2. And what we want to do is find if this is going to be the proper setup. So does each atom satisfy the octet rule for an N2? Well, 1, 2, 3, 4, 5, 6, 7, 8 looks good for this nitrogen. This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. All right, so it passed rule 1. It did check the octet rule. But did it start with the correct number of valence electrons? Well, if we redraw those electrons on those bonds, and remember, this nitrogen started off with, I'm just going to color code this, with these electrons. And this nitrogen started off with these electrons. All right, nitrogen only has, if we label this 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen only has 5 valence electrons, but over here it started off with 1, 2, 3, 4, 5, 6. And so did this one, 1, 2, 3, 4, 5, 6. So what we can say here is that, I'm actually going to type in the answer. Nitrogen started with too many valence electrons. So that's the problem with this one. Nitrogen started off with too many valence electrons. It started with 6 instead of the 5 that it was supposed to have. All right, problem 4b. We have a sulfur, silicon, and another sulfur. Check if each atom satisfies the octet rule. Well, this sulfur has 1, 2, 3, 4, 5, 6, 7, 8. This sulfur has 1, 2, 3, 4, 5, 6, 7, 8. But the silicon only has 1, 2, 3, 4. So that's the main issue here. Silicon, even though it does, the sulfurs do satisfy the octet rule, the problem here being that silicon did not meet the octet rule. Not only that, but sulfur did not start with the correct number of valence electrons, and neither did silicon. Silicon starts with 4, but in this case, we're seeing that it only had 2. Sulfur starts with 6, but in this case, it started with 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So there's actually 2 problems with this. So the first problem being silicon didn't meet the octet rule. And then the other problem being no element started with the right number of, I'm just going to put VE for valence electrons. I have to make this a little bit smaller. There we go. So silicon didn't meet the octet rule, and no element actually started off with the right number of valence electrons. All right, so what's the problem with 4C? Check if each atom satisfies the octet rule. Hydrogen only needs 2. This hydrogen is connected to 2 electrons, one right there, one right there. This hydrogen is actually connected to 4, so 1, 2, 3, 4. So that's an issue. This oxygen, does it have 8 valence electrons? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does, but it started off with the wrong number. Oxygen only starts off with 6 valence electrons, but over here it started off with 1, 2, 3, 4, 5, 6, 7. So, 2 problems here. The first one being that oxygen started with too many valence electrons, and middle hydrogen has too many electrons. You could also say that the middle hydrogen also started instead of oxygen. I'm just going to type in O. So the middle hydrogen and the oxygen started with too many valence electrons, and the middle hydrogen has too many electrons in general. All right, finally, 4D, we want to find all of the errors. Iodine doesn't meet the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Looks good. Nitrogen, however, only has 1, 2, 3, 4, 5, 6. So that's the first problem. Nitrogen doesn't have enough valence electrons. Now let's check also, did the elements start with the correct number of valence electrons? Iodine was supposed to start with 7. 1, 2, 3, 4, 5, 6, 7. So that looks good. 1, 2, 3, 4, 5, 6, 7. That looks good. 1, 2, 3, 4, 5, 6, 7. So the iodines, they're okay. They started with the correct number of valence electrons. Nitrogen, however, was supposed to start with 5. So there was one right there, one right there, one right there. It's actually missing 2 electrons. And if we actually added 2 more electrons, this would have been a correct diagram. So those 2 electrons actually belonged right there. So basically, it's the same problem as before. Nitrogen just simply didn't have those extra valence electrons drawn in. And that was it. All right, so that concludes practice problem number 4.